Magnetic field in this direction, but not in this direction. Now watch what we can do. Okay, now watch this. Now, as if that's not impressive enough, let's flip the track over and watch this. So the superconductor is so strong it can actually carry other things on it. Let's try to carry an orange. Levitating bread. So in order to understand how quantum locking works, let's first understand how superconductivity works. So if I were to graph here on the y-axis resistance, so this is just electrical resistance versus temperature. At high temperatures, the resistance would be high, but then suddenly it would drop down to 0. Now for the superconductor that I was using, this is around 0.01 ohms. And the interesting thing is this is exactly 0 ohms. So once it drops down to this lower temperature, the resistance of the material is exactly 0. Not really small, but 0. There's no electrical resistance. Now to make sure you know how crazy that sounds, imagine I were to tell you that I begin stirring this liquid here, and then I stop stirring it, and you can see that eventually it just stops swirling around altogether. But what if I were to tell you that there's a material that if I start swirling it, it never stops, ever. There's absolutely no internal friction. Well, that would sound preposterous, but that's exactly what's happening in superconductors, but instead of water flowing around in a circle, electrons are flowing around in circles. And it never stops. In fact, there's no internal resistance. So with semiconductors, you literally have perpetual motion of electrons once you start them moving. As long as it stays below this transition temperature, those electrons will flow indefinitely. But how is this possible? How could there be no internal resistance? How could the electrons moving around in a material not cause the material to heat up very slightly? Well, it has to do with quantum mechanics. Now, normally an electron in a conductor can be thought of as a free particle moving. So what that means is that the electron can move through the material and it can bump atoms in the material and bounce into them and get scattered. Now, when an electron hits an atom in the lattice of some conductor, what that causes it to do is lose some energy. So when the electron hits this atom here, it causes it to wiggle a little bit, and that turns into heat, and so the electron loses some energy. And so by moving electrons through any conductor, you eventually lose the energy to heat. So the current will stop as long as you don't keep pushing the electrons. So in a normal non-superconductor material, you throw electrons or try to move electrons through it, they're going to bounce around for a while, but eventually they'll stop. And the stopping comes because they're hitting atoms in there and they're moving around and everything starts jiggling and it turns into heat. But for superconductors, something interesting and weird happens. Once you cool it down to a very cold temperature, electrons stop acting like individual particles, and they actually pair up with other electrons. And the electrons don't even have to be close to each other. They can actually be hundreds of nanometers away, and they act like they have some type of mysterious force connecting them. And when the electrons are attracted to each other and pair up like this, it's called a Cooper pair. Now, a Cooper pair is interesting because normally electrons should repel each other, not attract each other. So let me explain why electrons could attract each other in superconductors. When an electron is moving through this lattice of ions, the ions are positive, the electrons are negative. So the electron moves, let's say the electron's moving in this direction. So as the electron moves through, it has a negative charge. The ions in here have a positive charge, and they're very large atoms, so they don't move very much, but they're actually attracted to the electron there. So you can see that as the electron moved through, it kind of attracted these positive ions near it. And so it pulled these positive charges towards it. So that an electron that's over here moving this way, it actually doesn't feel repelled by this electron, but it actually feels like it wants to go towards it because it kind of gathered these positive charges near it. So this feels a little bit attracted to the electron. Now the attraction is very weak, but what's interesting though is that even though it's weak, it acts over a long distance, so that these two actually act like they're two pairs together. So basically the only reason this is happening is because the electrons attract these positive charges that move towards it a little bit, which attract another electron a little bit. And that may sound like an insignificant thing that's happening, but it's actually very significant. What it causes to happen is that these two electrons stop acting like individual particles and act like one particle together. Now this new particle that forms, it's at its lowest quantum state. And in order to excite it to the next level, it needs a certain amount of energy. You can't just give it any amount of energy. It has to get to the next quantum level. This is another quantum effect because it means that you can't give something any amount of energy that you want. It has to come in discrete packets. So in order for it to be scattered, meaning in order for it to bump into anything, the thing that it's bumping into has to give it some minimum amount of energy. So there's some amount of energy that's a minimum that it has to receive. It can't receive anything less than that. So it has to be greater than some value that I'll just call x. So at higher temperatures, this Cooper pair, or these electrons, can move through and bump into the lattice and get scattered and lose energy. But what's interesting is if you cool it down colder and colder, eventually this value here of each individual atom becomes so low that it's less than the minimum energy needed to scatter this Cooper pair, meaning that basically anything it bumps into doesn't have enough energy to do anything to it, so it doesn't affect it at all. It's not like it affects it a little bit, it can't affect it at all. And so this Cooper pair can now move through the lattice unaffected in any way. The only way that it can affect it is if something bumps into it with enough energy to bump it up to its next quantum state. Now that can happen even at cold temperatures. If you flow enough current through it and get them moving fast enough at a high enough voltage, then it can bump into stuff at a high enough speed so that the thing it bumped into gives it enough energy to scatter it. So even superconductors, if you flow enough current through them at high enough voltage, you can scatter it and cause heat to form, and you lose some of the flow of electrons. So basically it's not a superconductor anymore. So now that we know how a superconductor works, let me explain how quantum locking works. So how we can get the superconductor to start flowing current in it is just move it towards a magnet. When you move it towards a magnet, it exposes it to a changing magnetic field. And when you have a changing magnetic field, that induces a voltage, and that voltage pushes electrons around in eddy currents in the material. That's the reason why when you move like a block of aluminum towards a large magnet, then that aluminum will slow down. So it's like it's moving through water or something, because it's causing small eddy currents to form in there, and that movement of electrons in there causes a magnetic field that opposes its own magnetic field that it's going through, and so it pushes against it and slows it down. So what that means is that when I move a superconductor towards a magnet, it's going to repel it. But that's not all we saw there. We noticed that it didn't actually repel it. We were able to turn it upside down, and it was attracted to the magnet. So it didn't want to only repel it, it actually just wanted to stay right where it was. And that doesn't happen with normal diamagnetism. So because of its superconducting properties, it makes it so that there cannot be a magnetic flux that goes through the material. So the magnetic field lines cannot go through it. So in a normal conductor, let's say we had a sphere of aluminum or copper or something, and this is our superconductor. If you could measure the magnetic field lines around it when you put it next to a magnet, this is what it would look like for a metal. The magnetic field lines just go right through it. But what's interesting for a superconductor, that's not what happens. Because the superconductor is forming these eddy currents in there when you move it towards the magnet, it's opposing the magnetic fields in there, and so it doesn't let any magnetic fields form in there. And this is a form of perfect diamagnetism, but it also is called the Meissner effect. So they go right around it. The magnetic field lines can't penetrate it, so there's no magnetic flux in the superconductor. Now this is a result of superconductivity, but this still isn't quantum locking. We're almost there. So this is a type 1 semiconductor, but what I have here is a type 2 semiconductor. Now type 2 semiconductors don't quite look like this. Type 2 semiconductors actually have impurities in them, and these impurities allow some magnetic fields to penetrate it. And the parts that it penetrates, it creates this magnetic vortex. It forces kind of a funnel down of the magnetic field lines. So for a normal type 1 superconductor, it can still move through a magnetic field just fine, because the magnetic field lines just flow around it. But for a type 2 semiconductor, it can't move through these magnetic fields because it gets locked into place. The magnetic field is funneled down through the center and it locks it. So in order to move through it, it has to push through those impurities. And so the only way it can move through a magnetic field is if the magnetic field is symmetrical, because then it just gets replaced with a new part of the magnetic field, and so it doesn't matter where it is in that field, it can just move through it. But any magnetic field that's not symmetrical, it can't move through it. So basically it's like it has these strings going through it, holding it in place. They're kind of like these magnetic strings that don't let it move. So in my experiment, I could move it like this on the track because it was a symmetrical magnetic field. And so it didn't matter where it was in the magnetic field. It didn't affect the lattice inside. There was no internal force on it. But when I moved it up and down, that wasn't symmetrical. That was changing the magnetic flux through it. And so it pinned it in place. So basically I had to put some force on it to drag it through the magnetic field lines. And once I stuck it there, then it stayed in that place. And once I stuck it higher, then it stayed in that place. And so quantum pinning is actually due to parts of the superconductor that aren't superconductive. And it makes a part of it that gets pinned in place due to the magnetic flux that's able to penetrate it in a few spots. It's actually more than a few spots, it's actually a few billion spots. So how this differs from a normal repelling force of a magnet is it's actually not repulsive or attractive, it's both of them. It just wants to stay in place no matter what. And so you can put it in anywhere you want and it'll stay there. Well, thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, remember to subscribe and hit the bell so you can be notified when my latest video is out. And thanks for watching, and I'll see you next time.